Okay. All right. So was online GDB, right? All right. So just as a reminder, back from, well, I'm actually just going to write it again here real quick. We talked about all programs begin and end with main. I'm going to put another reminder how humans solve problems. We use our memory. We ask questions and repetition. And I've mentioned that 100% of programming languages have facilities for these three things. So what we're going to introduce, well, we're going to look at our template for like our Hello World program in C++ here. I know we looked at that last time, and I'm going to show it again here real quick. That's kind of how I encourage you to start whenever you sit down to write a program in C++. Start with Hello World, run it, make sure it spits Hello World out to the screen. Then you have confidence that your setup is working. From there, what we're going to do today is we're going to introduce the way that C++ accomplishes memory, asking questions, and repetition. We're going to give ourselves some immediate tools, and then we're going to start looking at how those tools can be used together to solve some problems. Okay? And then what I want you to imagine here is, even though for most of you, this is your first experience with any sort of computer programming, so it's going to be, cryptic to you or whatever, but I want you to try to imagine if you were already a, competent programmer and you sat down to learn a brand new language. Let's say you were a C++ programmer and you were learning Python, as an example. If you can sit down and say, well, how do I represent memory in Python? How do I ask questions in Python? How do I do repetition in Python? If you can just figure out the syntax for those three things really quickly, you can now solve a bunch of problems using a language that you just started using 5 minutes ago. All right. So that kind of goes back to this idea that computer programming is our skill set. The language really doesn't matter. Okay. So human beings solve problems this way. So now for our C++ programming template, I'm going to switch this over to C++. I mentioned that to you last time, where you get this big drop down of languages that online GDB supports up here. I'm going to choose C++ here, but you can do Java, Python, any of these different languages. I think several of you have asked me if you can use other tools for doing your programming assignments in here. I'm fine with that, as long as in the end you give me a link where I can go and view your code somewhere. Online GDB solves two problems for me. One, I don't have to support 20 different installs of different software development environments, because it's all on a web page. And secondly, you can share this. It gives you a link where you just have to give me that link, and that's your code. All right. So when you submit your homework, you're not going to be submitting your code directly or a file. You're going to be just giving me that link with your self-assessment. We'll talk about that when we get to our first assignment. All right. So if you want to use a different tool, that's fine. Just make sure you use something like GitHub or something like that, where you can provide me a link. If you don't know what any of that stuff means, use this tool. All right. You'll eventually learn that other stuff, because we'll look at that in another class. But all right. So if we're doing C++, for example, we're going to include some libraries, and this is a pretty common cadence for all programming languages. Often a language by default brings some code in. So for instance, if I was, let's just look at If you remember, we had that chart that showed the evolution of our programming languages. We had C to C++ to Java, C#. So if I just flip this, I hit Java as my starting point. Notice the hello world program in Java is a little bit more concise. We're not importing anything up top here. I'm just using this as a quick lesson. This is fine. You'll find this in a lot of textbooks with the curly brace, opening curly brace here at the end of this line. I like it like that. I'm never going to take off points if you don't do it this way, but you can clearly see where the beginning of this function ends and where the end of this function ends. Similarly, where the beginning of this ends and the end of this ends. When it's like this, it's much more difficult to see, I believe. The reason this became popular is because a lot of code used to be just in textbooks and saving a line meant something. Okay, now with web pages, they're just infinite length, so you don't need to save a line anymore. But many of you might choose this as your go-to move. Sometimes it's chosen for you. A lot of our integrated development environments, IDEs that you use for programming, by default, they auto-complete your opening, closing curly braces, and they'll put the opening one on the same line as like your function definition. So it doesn't matter, but I would say that this is the preferred format with the opening and closing curly brace indented underneath each other. All right, but when we look at a more modern language like Java here, notice, just get rid of the comment crap up here. There's nothing imported up top. And this is because by default, Java brings in kind of this generic library of things that you commonly might want to do with programming. For instance, you commonly might want to write something out to the screen. That's kind of a go-to move in programming, right? All right, so it kind of makes sense that that might be something that's just available to you out of the gate without you having to do anything special. So that's why we don't have any in Java, it's an import statement, but that's why we don't have those in here for standard input output stuff. If we wanted to use other things like a random number generator, things like that, then we would need to do something like an import java.util.random or something like that. You know, and that will bring in that library. All right, but for in Java, you have your class. Here's our main method. All programs begin and end with main. Notice that main takes in an array of arguments, command line arguments. Did I show that last time, or I just started talking about that last time? Command line argument stuff. Just getting ready. Okay. So I'm just going to copy this real quick so I can paste it next to the C++ version of this. So I'm going to switch it back to C++. Oh, I need to. I'll just write it again. This is probably how they had it written. So there's our hello world. I'm going to change this up just a little bit. So first of all, notice that in C++, if we want to do input output stuff, we want to write something to the screen, we do need to bring in our input output stream library. It's not available to us by default. Now that library lives inside of this thing called the namespace standard. If I don't want to use the namespace standard, I would have to do this. I would have to say, where did cout come from? Oh, that's also in namespace standard. All right, so we're going to say that this is not necessarily very friendly syntax. So we would in general prefer to say using namespace standard there. That way we don't need to specify where those couple of keywords come from. Okay. Now I'm going to add a couple of things in here just for historic purposes. Typically with main, just like we had with Java. So here's the Java version of Hello World. Notice that main, this is a function. Functions can take in parameters, inputs. As it's written right here, this function takes in 0 inputs. Java requires there's always one input, and that's going to be a collection of strings. That's what this is, an array of strings. You don't have to know what that means right now. Historically, in C++, we would have that here, but modernly, we typically do not use what comes in here, but I'm going to show you what it's for. A lot of times we would say int argc char pointer argv, something like that. I'll still run it, still works. So this syntax is just fine. What's this for? We're going to say parameters are for command line inputs. And let me show you what that means. And like I said, this is going to be not something that's commonly used in modern programming, because modern programs, we typically don't run from the command line. You've seen me run most of the stuff from the command line just as testing stuff. And actually our early programs would be more appropriate to run from the command line. But if you actually think about what software looks like today, you think about things like Microsoft Word or Chrome or whatever, things where you click some icon and a graphic user interface pops up, and the way you interact with it is by hitting drop downs and clicking on stuff and things like that. You're not just looking at some black screen that's just spitting text out. All right. But we want to understand the foundation where these things came from. So I'll go into the terminal here. So I'll go ahead and bring in my Hello World program here. A lot of times what I would do is I'm actually going to go ahead and put it into the slides. I've mentioned something here about your C++ programming template. I think I can hide this, right? So, so there's your default Hello World program in C++. I would encourage all of you to memorize this. You know, this is a comment. So from the / forward, this is something that the compiler ignores. This is for human eyes only, so I'll take that out. Technically, for the way we write programs, you won't need this part, but I'm going to go ahead and say keep that for right now. I want to re-emphasize this idea of where our languages came from, especially since this didn't drop off in some more modern languages, even though it's rarely used. All right, so I would say memorize what you're looking at right here. This is your default go-to Hello World starting point for any C++ program. Okay, so whenever you sit down to write code, you start by just regurgitating this to the screen, hitting the play button or running the program, making sure it spits Hello World out to the screen. Then you know I have a working environment. Then you go and start solving the world's problems for the program you're about to write. All right, makes some sense? All right, so I'm not an advocate in general of memorizing a lot of things. A lot of stuff you can go and, figure it out or go and look at some documentation or something like that. But the starting point for programs in different languages are worth memorizing. So you can just plop down and get going instead of having to go and Google it or something like that. Okay, so let's go back out here. So again, we're having a throwback here to the early days of programming when we didn't have graphic user interfaces and your entire screen looked like this. It was just a big command line interface like that. All right. So I went in, I typed out my program. We're going to go and test this to make sure that I have a working environment. So I'm going to go ahead and I'm going to say, what is it? G++. What did I call it? Hello. CPP. So I'll compile it. So when I say G++ hello CPP, it's going to give me a file called a.out. That's my executable. I'll go ahead and run that, and there's my hello world. Okay, so from there, I now know that I have a working template for hello world and in C++. So now I can go back in and I can start writing the program I actually wanted to write. All right. But now let me show you what the purpose of these two parameters that can get passed into main are. All right. Again, all programs begin and end with main. So when I just ran that, what it did is it started at line 1 of main here, and it did the one thing I'm telling main to do right now, which is output to the screen, hello world, followed by an end of line that presses enter, kicks it down the line. All right. If you don't like the end L thing, there's other ways of accomplishing the same thing. I can do that, which is a line feed. I don't want to use the built-in end L thing. Doesn't matter. They all do the same stuff. All right. Now, what I'm going to go ahead and do is I'm just going to write a quick loop. Don't worry about the syntax for it. We'll talk about the syntax here in a little bit, because again, what we're going to try to accomplish today is we're going to introduce the way C++ accomplishes this, and this, giving us some go-to tools for solving a whole big collection of problems in this programming language, even though we don't really have the skill of programming yet. That's going to take some practice. I promise most of you are going to suck at it at first, so be prepared. That is going to be hard to catch on to, because like I said several classes ago, the problem with getting good at computer programming is, as human beings, we're too good at solving problems. We're not very good at articulating those little tiny baby steps of how to solve a problem, how to describe the solution to a problem. That's what we have to get good at in here, is breaking those problems down into smaller steps. The good news is the types of problems that we solve as computer programmers are trivial compared to the types of problems we solve as human beings. I used walking as an example, right? That's a hard problem to solve, yet it's not worth our full attention. All right, so I'm just going to write a quick loop. All right, so I'll go ahead and run this program. There's going to be no output. Oh, actually, there is output. The output, let me throw a couple other things in here and I'll tell you why there was some output. Notice the output is the name of my program. I'm going to go ahead and say cat dog or car dog. I guess let's just go with that. Whenever I make a mistake, it was for educational purposes. All right, so I'm going to go ahead and just add a couple of things after that. So now when I press enter, notice it spits out the name of my program, the first thing I said, the second thing I said. These are called command line arguments. You've actually seen me, if we pretend like this program ls, for example, which gives a directory listing. If I say ls-a, that gives me more information. If I say, whatever. So in that example, I'm running a program called ls and I'm giving it a command line argument -a for all. Show me everything, even the hidden files, all these things that have little periods in front of them. These are hidden files in the Unix file system. All right. So if we go back to the, I don't know, let's say the early 90s, it was not uncommon it was very common for our computer programs to take in command line arguments like this. This is how we got it to do things. In fact, even when I go and edit here, when I go to, type in my program here from the command line, I'm calling upon a program called VI, which is a text editor. Think of it like Microsoft Word. And I'm telling it the name of the file I want to edit. So it took in as a command line argument the hello.cpp, and then it made sure it opened the right magical file associated with that. Okay, so once upon a time, command line arguments were commonplace. Sometimes they actually still do exist today. If any of you have ever played around with a computer program, even on a modern operating system, and you want it to do a certain thing, and you go and Google it or something like that, it says, oh, you can actually tell the launcher to give it a couple of command line arguments, and it'll start up in like administrative mode or start off in some other thing. So programs today are compatible still with command line arguments. They're just not commonly used. All right, so let me explain what these command line arguments are doing and why. So in C and C++, we need two different pieces of information. Whereas in Java, I think I still have that. Nope, don't still have it copied. Nope, doesn't matter. If you remember in Java, what was inside main here was something that looked like this, string array args. And the string array args thing was equal to this dude. These two guys are the same animal. All right, this is a collection of strings, collection of words. So for instance, car and dog were two strings. Okay. Now in Java, this was enough to accomplish what we needed to accomplish. In C and C++, it's not, because these being older languages, this kind of thing here is called an array. It's a collection type. All right. In C++, this kind of array, well, we'll talk about pointers later, so let's not get into that right now. But let's just say this is an array. Arrays do not have the ability to advertise how many elements they hold in C and C++. It's just not a feature of that product. All right. Therefore, we needed another argument. This is you can name these variables whatever you want. argc and argv, you can call them whatever you want, but they must be an integer and a character array or a string array. But typically you name variables based on what they mean. These are the argument values. This is the argument count. How many of those values are there? Okay, so in C and C++, arrays are not capable of advertising how many elements they hold. So built into main, all programs begin and end with main. So the C++ runtime, when it calls main, it passes along to main how many command line arguments it found, and it also passes along the actual command line arguments. So then what I did for my loop is I just went through, I took I on a voyage between 0 and whatever argc was. So in our case here, argc was 3. I passed it 3 pieces of information: the name of the program, car, and dog, right? So there's 3 things. Each time through, I'm going to print out the value at bucket I. So this is going to print out whatever it found at bucket 0 the first time, bucket 1 the second time, bucket 2 the third time. All right, for my 3 arguments. So there was bucket 0, my first command line argument, bucket 1, bucket 2. If I don't pass it any extra stuff and I just run the program, you notice that in C++, the name of the program does get passed in. In Java, it does not. So Java, if I were to run the same command line program like this, it wouldn't actually have any output because it doesn't capture the name of the program. It just captures the extra stuff that were command line arguments. Okay. So in any case, that's the rationale why we have something like this that exists. Like we saw in here, by default, it left main empty here. And this still worked because typically, modernly, we don't use command line arguments. It's just not a common way we write programs today because people don't run their programs from the command line commonly today, right? I'm guessing many of you have never used a command line. It is a skill set that you're going to learn as a computer scientist because it's still very popular to run things from the command line, especially for like web programming type stuff. Or network programming. It's pretty common. You might be remoted into a router that's under the floorboard somewhere, and you don't have a very pretty graphic user interface when you're working with it. You're actually running Linux or something. But commonly, when you think about modern software, there's a lot of clicking on icons and drop-down menus and things like that. Not a whole lot of typing to start the program. Okay. Even though what's under the hood is still that whole typing to start the program thing. Just like you're seeing here. How do I run this program? I just hit this little play button that says run. Yet we're seeing out here that the cadence for running this guy is to compile it first, then I can run it. That's what's actually happening behind the scenes in this guy when I hit run. That makes sense? Okay. It's not like it's changed. They've just hidden some layers from us. And notice here, I can give it command line arguments. If I put that guy back in here, and I do a 4, it dies 0. I do my car dog thing here, and then I run it. There's my car dog with the A dot out. And so you can accomplish it inside of online GDB. Okay. Now I'll go ahead and throw this out there. This is not something I'm going to test you on, but it's something that is really important that you understand. I like to build a strong foundation before I teach you the stuff that's actually applied in today's world. Okay, instead of building a building on top of quicksand, we're going to have a strong foundation where we understand how things used to work, appreciate that they still work that way, but a whole lot of stuff happens for us. And then what we're actually going to be focusing on is the applied computer programming stuff where we're producing modern software. All right. For those of you who drive a car, you know, historically, you used to have to get outside the car and crank the engine to get it started, like a modern day lawnmower where you're having to pull the ripcord, right? Okay. Well, now, you know, and then even more modern, or less modern, but more recently than that, you used to have to hit the gas pedal a couple of times to get some fuel going in there. If any of you have a boat, you know, you still have that for some of the boat engines where you got the little bubble. You got to squeeze it to get the fuel going in there before you can turn the ignition so it actually has something to ignite. Then you have the fuel injected motors, the newer ones where you turn the key and it automatically does the little bubble squishy thing, right? And our modern cars have starters inside of them where instead of you having to get out and crank something or pull some ripcord, it's got this device in there that runs off the battery that does the spinny pulley thing for you to start the engine. All right. All that old stuff is still happening. You're just not the one doing it. All right. That makes some sense. Same thing's true in our modern software. We haven't changed that much. We've just hidden a lot of the details. And this really comes back to the argument of why a college degree in computer science rather than like going to one of those boot camps. One of those boot camps is going to teach you how to be a computer programmer. It's going to teach you a skill to write applied software. And you probably can solve 85, 90% of the problems with that. No problem. It's that last 10 to 15% where you're getting to a complex problem that requires a deeper theoretical understanding of how computers work and how the software is actually running and all this other jazz, where if you don't have this baseline knowledge, things like this, you won't have the competency to solve that problem. Now, somebody else on the team might. And that's okay, but that also then limits how far up you can move, right? Because you're going to be the worker bee person, and you might be really, really, really good at that. My wife has a computer science degree, but she's been a COBOL developer since 2000, and she's a worker bee mentality. She doesn't want to do the extra crap. Tell her what you want her to do, and she'll sit there and do it. And when she's done, you tell her the next thing. She doesn't want to manage people or anything like that. Now, when you've been at a company as long as she has, you end up accidentally having to manage people, but it's not what she wants to do. All right. And believe me, managing people is not all it's cut out to be. It's one of the reasons I sold my company. But now I have, all these CS faculty people to deal with. What's this? Okay.
They just keep trying to get him to manage people.
Yeah. Yeah, well, I mean, I'm pretty good at doing it. But you get pulled in a lot of different directions is what ends up happening. When what I actually enjoy doing is sitting in front of a classroom teaching the crowd, not a lot of the paperwork stuff. Is what it is. Okay, so questions about this whole command line argument thing and why this crap even exists. And we really see it as evidence. We had that little chart that said, we had C, then C++, then Java, C#. We had over in the, this Objective-C and the Swift stuff on the Mac side. But we seen the evolution of programming languages all kind of coming from that C programming language. All right. And this stuff is still there. Java, it's required. So we still see it in Java, and Java doesn't let you take it out. No problem. But that's what this crap means. There's many, many, many Java programmers. Again, using our example, let's say people who go through one of those, 3-month boot camps for becoming a Java developer, where they've written that Hello World program as a baseline 200 times, yet they've never actually used command line arguments. It's not common. But maybe it's something that could be useful every blue moon or something like that. All right. So now that we have our baseline C++ programming template, you're going to sit down and write a program. And you're just going to start with this and hit play and make sure it does what it needs to do. I'm going to go ahead. I'm going to steal that slide. I'm going to call this guy the mapping. I think we already have this slide someplace else, but I'm just going to write it again. So again, this is how human beings solve problems. The job of a programming language is to allow us to tell this dude what to do. So 100% of programming languages have facilities for these three things. Memory is done through something called a variable. Asking questions is done through conditionals. Repetition is done through loops, and I'm just going to say functions. Methods are equivalent, whatever, just go with functions for right now. All right. Once you learn these three concepts in some language, you can already solve a whole bunch of problems. Now, you might have to go and look into some libraries to see, oh, this language has some built-in stuff for, like, for instance, PHP. The PHP programming language, it's meant for web developers, and it has a bunch of convenient library tools for talking to databases easily. So like one of the common databases in web development is called MySQL. So you can connect to a MySQL database in like 2 lines of code with PHP. So you got to go and look up what's the library you got to use for that, blah, blah, blah. That's something that's going to be kind of unique to PHP. But You can still write a hello world program in PHP and loop through stuff and things like that using just these tools. So programming languages do differentiate themselves somewhat after the basic core concepts. But the way that these languages differentiate themselves leads more to what language is the right tool for the job, rather than us saying which language is better than some other language. Certain languages lend themselves to certain things better than another language does. All right, so this is the mapping for this. So let's look at variables. So we're going to remind ourselves here that C++ is a strongly typed language. This means that when we create a variable, we must define what kind of value that variable is built to hold. All strongly typed languages require this. Okay? Actually, that's true where it matters. You've already heard me make fun of Swift, where you can have variables named with emojis and stuff. Technically, Swift is a strongly typed language. When you define a variable, if you don't put the type in front of it, the first time that variable is used, the system will determine what kind of value is in there, and then that's its identity from that point forward. But generally speaking, this is a true statement. And I would even say with Swift, if you know a variable is built for holding an integer, just go ahead and tell it. This is going to hold an integer. Okay? So syntax for this is type followed by var name equals value semicolon. Technically, this equals value portion here is optional. You can define a variable and not put a value in it with the expectation that you'll load it with the value later on. That's possible. But a high percentage of the time, when we create a variable, we're probably going to give it an initial value. I'm a big advocate. Programming languages, they do give you default values for variables. Let me show you that here real quick. So I'm going to go ahead and define int age is equal to 15. So my type here is int for integer. The name of my variable is age, and I'm setting it initially equal to 15. Okay. And then I'm going to say int my val, and then put a semicolon there. So I'm not going to actually give it an initial value. So now if I go out, if I come down here and I do cout, now you're going to kind of see what these arrowy things are for. It allows you to build up a string. So I'm going to say age is equal, well, let's just say age equals age. Something like that. I'll go ahead and run it. So you see age equals 15. But the only reason it says age equals is because I wrote that here. If I leave that part off, I'm just going to get the 15. All right. I decided to add some extra commentary to my output, so it had that extra string as part of my output. Now, if I do cout my val equals like that, notice that my val does have a value. Default value was 0. Go ahead. It's end of line. It's like a built-in thing that's equivalent to carriage return, line feed, like that. If I didn't put that there, It's not illegal. He would just run these two lines together. They would just be sitting right next to each other. Yeah, so it's for formatting, for visual, for us seeing it, what's being spit out to the screen. And again, for modern developers, we're typically not digesting our software from a command line like this. So typically this whole idea of doing carriage returns and stuff is not necessarily a common thing, right? It's typically you just have some label that's going to have, a couple of things on it on your screen. And if you want to have two different things, you just have two labels on top of each other. All right. So in any case, we saw that. Oh, let me throw the endels back in here, or I'll just show you the two options. Notice that when I defined my variable called myval, which is of type integer, so I've described to C++ that this bucket right here, this named place in memory, is built for holding an integer. That's the kind of value it holds. All right, but I didn't give this guy a value, yet when I printed it out, it had a value. Its value is 0. That was the default value for integers. Yes, every programming language will give a default value to a variable, even if you don't put one in there. Some languages will at the very least give you a warning if you try to use a variable before you give it a value, Older languages like C and C++ don't. They just assume, hey, you must know what you're doing. It's kind of the reason why I pick C++ in here. Is I don't want it to let you get away with too much. More modern languages protect the programmer a little bit more, which you'll appreciate later on, kind of the fuel injection, turning your car on idea. But right now we want to be uncomfortable and have to get out and crank the engine before we can turn it on. We want to actually feel all the little details so we appreciate the more modern languages and all the stuff they're doing for us. All right. So even though this works, if I wanted my val to start off as being equal to 0, I should put a 0 in there. You should always take responsibility for putting the value you expect your variable to start with into the variable. Don't just rely on the default value, because you never know if they're going to change the compiler so that the default value becomes a 1 or a -1 or something like that. It's never too late to update C++. They actually have updated C++ several times. You see it here in 2014, 2017, and then actually no, yeah. And then 2020. Yeah. They have, but they didn't change the default values. But you never know. For example, they made more modern versions of arrays that know how many elements are in them. As an example, kind of let's keep up with some of these other languages, because an important thing here, especially when we're talking about a language like C and C++, C++ specifically, is this is still a commonly used language today. It's becoming maybe less and less common, but in any sort of application that you need to be fast, C++ is probably your best choice, or C. Both of these are compiled languages that go down directly to working with the hardware. Java, at some levels, interpreted. Even though it's a compiled language, it goes through the Java virtual machine. It gets interpreted at runtime, where it converts from code that runs on this piece of software, a computer made of software, and translated to what runs on your hardware. That one extra level of translation slows it down a little bit, which is why our modern video games are not written in Java. Okay. Not that Java couldn't handle a whole bunch. I mean, Angry Birds would be fine in Java. Okay, but maybe your latest, greatest, first-person shooter or something would be a little sluggish, or you'd have to cut down on the number of explosions or something like that. So C++, super fast language. You're able to fully take advantage of your computer's hardware. Still very popular, but modern programmers are desiring some of these quality of life features that are in our more modern languages like C# and Java. So when they go back and they add stuff to old languages, they don't really change these types of things. What they do is they add new structures that accomplish the idea of having collections of strings, for example, but specifically a collection that can report how many elements are in it, rather than you having to pass around two values. You know, here's my collection of crap, and we'll talk about how that can be navigated when we get into pointers and memory and stuff. But just understand that this guy has some complications behind it that exist in all of our modern languages, but it's much more obvious to us here, where we actually have to walk through memory, one little bucket at a time. But in old style C++, we have to pass around two different values. Here's my collection of stuff. Here's how many things you'll find in that collection. Good luck. All right. So first lesson there, when you define a variable, give it a value. If you expect it to start off as 0, put a 0 in there. Don't just rely on the default value. Make some sense? Okay. Now, let's talk about these types. Possible types. All right. So you've seen me create an integer. Now I can come in here and I can say char C is equal to an A. Notice that characters have a single quote before them and a single quote after them. This is the char literal A. This is the int literal 0. This is the int literal 15. All right, so I can create a variable named C of type char, which is character, and I can set it equal to A. I can create a float. Actually, I'm going to go ahead and create a double instead of a float. Call this guy pi 3.14. So doubles know how to hold decimal point values. Go ahead. What's it? We're about to talk about it. You're asking what's a double? Yeah, we're about to talk about it. Well, the actual details of it. For right now, what I want you to understand is it can hold numbers that are more than integers. Like with a decimal point value, 3.14 or something like that. It's a double precision floating point value. So we can call this guy pi 2. Integers can only hold whole numbers. So I can't put a 15.4 inside of an int. It doesn't know how to hold the decimal point part of it. Go ahead. Same thing as a double, but can't hold as much. It holds smaller values. And that's what this next slide is going to be. It's going to detail what each of these are. I'm just showing you kind of a hodgepodge of these are some of the things you can create. So these are our different types. So when we look at our possible types here, we have something called a byte, short, int, long, float, double. And these are all, they don't have capital letters in front of them, but it's adding capital letters. Bool, which is a little bit weird in C++. Actually, I'm going to put char before bool. Let's go with that. All right, so these are our, let's call these our possible types. In C++, we also have something called a long. That'll make sense here in a second why we have those. All right, so let's talk about the kinds of values each of these can hold. Bytes can hold whole integers. Shorts can hold whole integers. Ints can hold whole integers. Longs can hold whole integers. Chars can hold whole integers. Let's just focus on all those for a few minutes. Forget about floats, doubles, and bools for a second. So an integer is a value that doesn't have a decimal point. So like 3 or 7 or 29, these are integers. All right. Why do we have so many different ways of holding whole integers in our modern programming languages? And by the way, these types, these are the same types in C, C++, Java, C#, Swift. These types have persisted over time. Sometimes instead of bool, it's called boolean. Spell it out, you know, that kind of thing. But why do you think we have so many different ways of storing whole numbers? Go ahead. Okay. Why do we need memory efficiency?
I mean, it's not as important.
Yeah. Yeah. So we looked at in here that memory used to cost a lot of money, right? I think I gave the example of an 8 megabyte chip was $1,000 and something like kind of 1994, I think ish, something like that. So our computer memory used to be much, much, much smaller. And as computer programmers, we had to be very careful. We had to make sure that, you know, if we only needed to hold a number between 1 and 10, we wanted to pick the variable type that used the smallest amount of our computer's hardware memory in order to hold those, because I knew what the limitation of my values were. Okay. Now, we've already learned what bytes are. What's a byte? 8 bits. All right. So this is a 8-bit signed whole integer. Signed means it can hold positive and negative numbers. Because that kind of makes sense, right? When you want to remember something, we might want to hold whether we be able to hold -12 or positive 14. Should be able to hold both sides. But keep in mind that if we want to hold negatives, we're going to need one of those 8 bits to keep track of whether it's positive or negative. All right. It's a little bit more complicated than that. It's not just the bit. It turns into something called 2's complement, but you'll learn about that in 325, or I might accidentally tell you about it at some point in here. But for right now, what does 8-bit signed whole numbers mean? It means it holds values in the range of -2 to the 7th power to +2 to the 7th power. Technically, it's +1 on that side. So this is -127 to +128. That's the range of values that will fit inside of a byte. I'm gonna steal this line here. A short is a 16-bit signed whole integer. This is 2 to the 15th to 2 to the 15th. This is -32,760. Actually, it's the 8's on the other side. So this is -128 to +127. -32,768 to +32,767. That's the range of values that fit in there. Short, or I'm sorry, an int is 32-bit signed integer. 2 to the 31st, 2 to the 31st. So this is -2 billion. It's like 2.1 billion to +2.1 billion. Something in that ballpark. You do the math on it, 2 to the 31st, there's your 2.147 billion. And again, it's only to the 31st power instead of the 32nd because we're holding signed numbers. We need one of those bits to keep track of whether it was a positive or a negative number. A long is 64 bits. signed whole integers. So this is 2 to the 63rd. 2 to the 63rd. So this is negative big to positive big. I think it's like 16 quintillion. So 2 to the 63rd. Oh, 9 quintillion. 9.22 quintillion. Hey, but what if that's not big enough? C++ supports a long, like I said, which is 128 bits. Modern object-oriented languages, if you do need to hold a bigger number, you just flip over to objects. For instance, Java has an object type called big integer, which can hold arbitrary size integers, but the bigger the number gets, the slower it gets because of what it's having to do behind the scenes to do math. All right. All right. This all makes sense? Now, realistically, like he said, this used to be a much bigger problem than it is today. As computer programmers, we really should be good stewards of our computer's memory and always pick the variables that are most appropriate for the values that we're storing. But we don't mind bullying computers a little bit. We're all kind of jerks when it comes to that. It's like, look, this computer here has 64 gigs of RAM in it. Look, I don't care if I'm a little wasteful. That's a lot of integers I can store in 64 gigs of RAM. So generally speaking, if we want to hold a whole number, we use int. And if that isn't quite big enough, we use long. And if that's not quite big enough, because we're doing some kind of sciencey simulation type thing or something like that, where the numbers get gigantic, then we probably look at the libraries for the language we're working with and find out what do they have to facilitate even bigger numbers. Most of our modern languages have some kind of supersize me function in there for dealing with gigantic numbers at the cost of some performance. That makes sense? But as a modern programmer, I would say 98% of the time, we're going to be using int for holding whole integers. And every now and then we'll kick it up to a long if we need bigger numbers. But a majority of the problems that you're going to solve as a programmer, you won't need bigger numbers than an int. Like I said, unless you're getting into some weird sciencey, simulation-y type stuff that is just focused around the whole number idea. If we're just counting some kind of things, most of us are going to stop counting way short of 9.2 quintillion. We probably stop caring somewhere in the high 100,000s, I think. It's just no longer important. All right. So let's look at chars then. A char, well, actually, chars are a little bit different in different languages, but in C++, a char is a 8-bit unsigned whole integer. So this is 0 to 2 to the 8th. 0 to 255. But wait a minute. I just showed you back here that a char holds characters, where characters are denoted with single quotes around it, like an A or a B or a question mark. Okay, these are all characters. Why are chars 8-bit unsigned whole integers? Anybody know? Go ahead.
Our characters represented by whole.
Yeah, so computers like numbers, right? It's kind of their thing. Human beings, we like words and things like that. We're okay with numbers as long as they're base 10 numbers, but we have some comfortable types that we're used to. Computers, they store numeric values. That's what they're good at storing. So even though as a human being, when I create a variable of type char, I mean for there to be stored an A or a B or a question mark. That's what I intend to store. But behind the scenes, the computer is going to hold that as a number. And then when you go to use it, it's going to map it to the correct kind of value. Okay. So in C and C++, it uses an 8-bit scheme. Java and C# and Swift use 16-bit numbers. Do you know what the 8-bit number system is called? Oh, the 8-bit char. It's called a character set. The 8-bit char character set. Do you know what it's called? ASCII. That guy is for 8 bits. So if you were to go on to the internet here and look up the ASCII table, it'll bring up something like this. Oh, there we go. We're going to get a higher resolution. There we go. So here's the decimal number and the character. So we see an uppercase A is the number 65. An uppercase B is the number 66. A C is the number 67. A D is 68, so on and so forth. Okay, so it's looked up. When we create a char, if we put an uppercase A in there, it's going to store the number 65. But it's also going to know that its type is a char. So when we go to actually use that value, it's going to go and look it up on this chart and spit out the A instead of the 65. Does that make sense? And we can see that here. So here, I'll switch this to an uppercase A. So I'm going to just spit out the A here. So there's my A. Now on the next line, I'm going to put a little parentheses in parentheses before that. What I'm doing here is I'm telling C++, treat this variable as an integer. It's called typecasting. And you're going to see that this gives me the 65. There's my 65. So I'm proving what's actually stored under the hood there. Go ahead.
If you were to print C after the integer, reading it, your legacy would be like star, or
What do you want me to do?
you take the new C and put it after the integer C.
If I do this,
You want line 13 after line.
Yeah. If I were to
oh, it doesn't make a difference. It's not changing C. Yeah. So this will be A65A. Yeah. This just says for the moment here, treat C as an int instead of the value that's in there. Well, don't map it on the ASCII table. Make sense? Now, this also then means you can do fun things like loops. So I can do something like for char C is equal to A, or let's say C is less than or equal to Z, C++. Already, let's call this guy C2. Since I already had a variable named C up here. So I get the whole lowercase alphabet. And why is that? Well, we just looked at the ASCII chart. Where's my lowercase a? It's higher. So it's a 97 as an A. Plus 1 is a 98, which is a B. Plus 1 is a 99, which is a C. Plus 1 is 100, which is a D, so on and so forth. It's a number. You could do math with chars. Now, it doesn't make sense to do math with chars, If we wanted to have a number stored and we wanted to do math with it, we'd probably store it as an int. The point is what we're seeing here is that under the hood, computers like numbers, and they're going to store everything as a number at some level and then map it back to something that the human being's not going to beat it for, later on, because again, we don't mind bullying the computers. All right, that makes some sense, how chars are stored. And then, so the older languages, C and C++, they use the 8-bit scheme, which is ASCII character set. Old ASCII, actually, you're seeing here only goes up to 128 unique. Extended ASCII goes up to 256. Okay, that's when you get some of those smiley faces and there's playing cards and stuff like that. Because, in the early days of computer programming, they actually thought the only language that existed on the planet was English. Can you believe that? At least we've changed today and we don't think English is the most important language. I've traveled to a lot of countries and promised that they basically just assume you're a dumb American and they just will speak English to you. I've tried to learn some of the languages. I tell all my grad students I'm fluent in all of their. So like in India, there's even towns right next to each other, if they're in different states in India, speak different languages. So like Hyderabad, where a lot of our grad students come from, they speak Telugu. And right next to there in the state of Tamil, the language is called Tamil, and it's not the same language. It's not like us speaking, Midwestern English compared to like somebody in Texas with a little bit of a draw or something like that, or somebody in Boston with a heavier accent. No, it's completely different words. But I tell them that I'm fluent in all their languages. I just know the bad words. So in any case, if in our more modern languages, once we decided, there's actually other natural languages in the world other than English, we needed to have a larger character set to represent, the various symbols and things like that from other languages. And that's something called Unicode. Okay, so Unicode has 65,536 unique characters in it. So if we were talking about a char in Java, for example, this would be a 16-bit unsigned whole integer. So this is 0 to 2 to the 16th, which is 0 to 65,535. Which I think you'll find if you add these two numbers together, that's what you get. So that means we have 65,536 unique characters in the Unicode character set. Doesn't cover every language on the planet. You have some pretty unique languages in like sub-Saharan Africa and things like that with a lot of clicks and stuff, but it does a whole lot better than ASCII did. Let's just go that route. But under the hood, it's still the same thing. Just 16 bits instead of 8. It's still doing a mapping. It's still holding a number. And then when you go to use it, it looks it up on the appropriate lookup table. C and C++ just are old enough languages. They happen to be based off of ASCII. In a more modern C++, there is a way of creating a Unicode character type. There's a new type specifically for Unicode characters so you can represent those other symbols. All right, that makes sense? And does it also make sense why a char is unsigned? We don't need to hold the number -100 when the ASCII chart starts at 0 and goes to, let's say, 255. This shows 127, but goes to 255 if you want to get to the playing cards and stuff. All right, makes sense? So we decide, hey, we're going to use the entire what's called bit space. We're going to use all 8 bits to hold the value because we don't need to keep track of a positive or negative sign. All right, so we'll come back on Thursday. Remind me our starting point here. I'm just going to say start here. We're going to talk about floats and doubles. Hint, a float is like an int. A double is like a long. So it's a bigger floating point number. And Booleans are trues and falses. And then we'll look at conditionals and we'll look at loops and we'll hopefully have our first programming assignment over the weekend. Questions, comments, concerns, bribes? And I'll see everybody on Thursday night too for the tech talk.
So for, okay, so forgot to do the finger catch.